Hey guys, and welcome back to another video on the channel. In today's video we're going to be going over an introduction to the chain rule for differentiation. So the chain rule is pretty much used when you have a function inside another function. So for example, if I like the equation y equals let's say 5x plus 6 all to the power, let's say 5, I've got pretty much two functions here. I've got my outside function, which is the to the power of 5, and my inside function, which is the linear term in here, 5x plus 6. Okay, so if you want to differentiate it, pretty much what you got to do is apply the chain rule. So pretty much this is differentiate the inside and differentiate the outside. So what we would typically do here is let our inside function equal u. So we go u equals 5x plus 6, and then we replace our y in terms of u. So we'd have y is equal to u to the power of 5. Then what we want to do is differentiate the inside. So what we're going to apply is the chain rule here. So what this pretty much means is, alright, if I find du dx and I times that by dy du, we can see those du's cancel and we get dy dx as seen here. So if I differentiate this, I'll have du dx. So what I'll have here is just 5. And here I'll have dy du, which will be 5u to the power of 4. So therefore dy dx is du dx times by dy du. So we have dy dx equals 5 times by 5u to the power of 4. And we know what u is. So u was established to be 5x plus 6, so we can put that back in there. So what we're going to have is dy dx is 25 5x plus 6 to the power of 4. So pretty much the reason why we do this is because expanding something like this is ridiculous because it's to the power of 5, and if we add it to the power of 50, that'd be even more ridiculous. So applying the chain rule allows us to break up functions like this. Okay, so pretty much here's the two notations for it. So there's the top one, Leibniz notation, I think that's how you pronounce it for chain rule, and then we have function notation. Either one is fine. I prefer pretty much the top one because the substitution makes more sense, but I'll show you how to use it for both of them. So pretty much what we have here now, let's understand what this means. So if you have f o g and you have x here, what that pretty much means is f of g of x. So you can see you've got your outside function, which is f, and your inside function, which is g of x. Okay, so if you see that, that's pretty much what that means in mathematical notation. So pretty much the chain rule here is, alright, differentiate the outside, so you have f dash and leave the inside function, multiply the differential of the inside, which is g dash of x. Okay, so remember, if you have f of x and you differentiate that, you write it with a dash pretty much, so it'll be f dash of x. Okay, so that's pretty much the notation of it. Let's get straight into pretty much some examples, more chain rule. Okay, so find the derivative of y equals 3x plus 4 to the power of 20. So what we want to do is, alright, let's establish what's our inside function. So we have y equals 3x plus 4 to the power of 20. So what I'm going to do is, alright, I'm going to write my chain rule here. So dy dx is equal to du dx times by dy du. Okay, so what I'm going to do is identify what u can be. So u is your inside function, so it's right in there. So I'm going to go, alright, let u equal 3x plus 4. Then I'm going to have, alright, y will then be, replace that with a u to the power of 20. Okay, so now I've got two of them, my inside function and my outside. So now I'm going to do is find du dx. So I'm going to differentiate this with respect to x. So I'll have du dx equals 3. Differentiate this with respect to u. So I'll have dy du. Using the power rule, bring that down the front. So you have 20 and subtract the power by 1 to the power of 19. So therefore dy dx is going to be 3 times by 20 u to the 19. Now, we know what u is. We established that to be that. So it's going to be 3 times 20 is 60. So you're going to have 60 brackets are u, which is 3x plus 4 to the power of 19. And that is the derivative of this function here. Okay, and that's all the working you need to have with it pretty much. If you don't want to do the substitution, just apply differential inside and outside and then you'll be all good. But for this video, I'll be showing you just using the substitution. That way you have all the steps pretty much. Okay, let's move on to the next example. So differentiate the following. Alright, so we have y equals 4x cubed minus 5x. the power of negative 2. So we have a negative power, but it's the exact same rule. Now, another way they can rewrite this is like this. So all they've done is flip this to have a negative exponent so you can clearly see the chain rule. But when it's originally looking like this, it's very hard to spot if that's a chain rule or not. But all you got to do is flip it to a negative exponent and that's the same pretty much rule. So our inside function is here. So I'm going to write our chain rule real quick. So dy dx equals du dx times by dy du. Differential of our inside, so let u equal 4x cubed minus 5x. Therefore, y is going to be u to the power of negative 2. Okay. Now, when differentiating with negative exponents, it's the same rule. Bring the power down the front, subtract the power by 1. Okay. So here we're going to have du dx is going to be 4 times 3 is 12, x squared minus 5. And here we're going to have dy du equals minus 2 u to the minus 3. Okay, so I've moved that power down the front and subtracted the power by 1. Okay, so that means dy dx is going to be 12x squared minus 5 times by minus 2 u, which is 4x cubed minus 5x to the power of minus 3. Okay, so the way you can just rewrite that is go dy dx is just, well, negative 2 times by, and then you can write both those brackets, so 12x squared minus 5. I'm going to move some stuff really quickly because I've run out of room. Move that. Then you got brackets, just here, 4x cubed minus 5x to the power of minus 3. And if you really wanted to, you could actually just write it like this with a positive exponent and just write it over a fraction. So if I got rid of this now, that's another way you can write it. But either way is fine, and that's its differential. Okay, let's move on to the next example. Okay, so find the gradient of the curve y equals 16 over 3x squared plus 1 at the point 1, 4. Okay. So pretty much we've got to differentiate it and then substitute our x value. So we have y equals 16 over 3x squared plus 1. And what we've got to do is differentiate that. So I can rewrite this as 16 3x squared plus 1 to the power of negative 1. And now I can differentiate that. So I'm going to rub this out and just chuck a y next to it. So first of all, we've got to identify our inside function. So our inside function is here. So we'll go, all right, let u equal that. So if I let u equal that, that means y is going to be this, and replace that blue bit with u, 16 u to the negative 1. Now I've got to write my chain rule as well. Du dx times by dy du. Now we've got to differentiate this. So du dx is going to be 6x, and here we're going to have dy du minus 16 u to the minus 2. So that means dy dx equals 6x times by minus 16 u to the minus 2. So therefore we're going to have 6 times minus 16, I'm not fully sure what that is, I'll put that in my calculator, minus 96x all over u squared, so 3x squared plus 1 all squared. So the reason why I moved the square down here is because it was a negative exponent, and that's it. So that's my dy dx. So I'm just going to rub this stuff out because we're not done yet. So I'll move that. Now, the question is finding the gradient of the curve at the point 1, 4. Now, it doesn't matter what the 4 is, only matters is what the x value is. So when x is equal to 1. So all we're going to do is substitute x equals 1 into our equation here. So we're going to have dy dx when x equals 1, and we'll have minus 96 times by 1 on brackets 3 times 1 squared plus 1 all squared. Now we substitute that. You can put that in your calculator if you want, or you can work it out. So we're going to have minus 96 on the top Then we're going to have 4 squared on the bottom, which is 16. So we have minus 96 on 16. I think that's divisible. I'm not 100% sure though, so I'll just double check. So 96 divided by 16, and that turns out to be minus 6. And that's how you would answer that question there. So find the gradient of the curve with the equation y equals 16 over 3x squared plus 1. Okay, let's move on to the final example of today's video. So all this is another question. They've just used a different notation. So this f dash pretty much is equivalent to dy dx. Okay, so we'll be using the different notation. So at the start here, where they have it like this. So we can see at the moment we have our inside function and our outside function. So in other words, we've pretty much got this scenario. So we've got f of x is equal to g of hx in this case here. So hx is your x squared plus 1, and your g of that is the cubic term. So if we're going to differentiate this, we need to differentiate the inside and the outside. So f dash of x is equal to g dash of hx multiplied by h dash of x. So that means we've got to differentiate the outside. So if you differentiate the outside, the 3 will come to the front. So you have 3 brackets, leave all that, x squared plus 1 minus 1, so it'll be squared, times by a differential of the inside, which will be 2x. So that can be simplified to 6x x squared plus 1 all squared, and that is your f dash of x. Okay, and that's it. I hope you enjoyed this quick little first video. So this is introduction to the chain rule. I'll be doing the second part where we'll be covering all these examples here, and then yeah, that's about it. I'll see you in the next video.